Yeah, so while I have the chance, I'd like to thank the organizers for organizing this nice boot camp and for giving me the opportunity to give a talk. So yesterday, in the first part of this tutorial, Ivona set up the basics of Markov chains, and then I talked about one particular method for bounding the mixing time of a Markov chain, coupling. And we're going to continue on that theme today. So in particular, I'll talk about a Markov chain for sampling from colorings of a graph, proper colorings. And we'll look at a coupling argument for bounding the mixing time. And once we once we have this argument in place, we'll look at it a little bit more closely and see in what ways the analysis can be made a little bit more clever, as well as simplified by a technique called path coupling. And then in the end, I'll talk about exact sampling algorithms. So far, what we've seen is that coupling allows us to give bounds on the total variation distance, so you're guaranteed to be within, say, some epsilon of the stationary distribution, but can you use a Markov chain to get exact samples? So that's the question that we'll talk about. Okay, so before I get into all that, though, I wanted to make a few remarks about what I said yesterday. So number one, yesterday we saw an order n squared upper bound on the mixing time of shuffling by random transpositions. And I should have mentioned that actually the mixing time is known to be of order at most n log n. And there's lower bounds as well. And this can be proved using strong stationary times, which at a high level are random times where you're guaranteed to be at the stationary distribution. So when I talk about exact sampling, if we have time, I'll say something about that. And the second thing is that I skipped over how to construct a maximal or optimal coupling which achieves the total variation distance. And even though that's not going to be necessary for anything that we'll do, it's pretty easy, and I think it's useful to know. So you want to construct a coupling of two distributions, mu and nu, which achieves the total variation distance. So you want to define random variables x and y, so that as far as possible they're equal. So what would you do? Well, kind of looking at this picture, you seem to have probability delta. What is this called? Gamma, where you can make these two be equal. So how would you do that? You could say with probability gamma, choose x to be equal to y, and according to the distribution, which is minimum of mu of x and nu of x, but normalized, so we would normalize it by gamma. Okay, and what do you do with the rest of the probability? So with probability 1 minus gamma, just choose x and y independently and sort of put them in these regions, by which I mean choose x according to mu of x minus nu of x and normalized. So this, and independently, for example, you could choose y according to mu of x minus mu of x. Okay, so it's pretty straightforward to construct an optimal coupling. Okay, so let's start with a Markov chain for sampling colorings. This is something that Ivona introduced yesterday. So we have a graph G with vertex set V and edges E. And the state space of the Markov chain is going to be omega, the set of proper colorings of G. And we're going to use a metropolis Markov chain, which does the following thing. You select a vertex and color pair uniformly at random. So uniformly random vertex, uniformly random color. So for example, maybe you selected that vertex and that color, and then you check, is that color something you can update that vertex to, by which I mean that it does not appear in the neighborhood of that vertex. And if that's the case, then you update it and and you go to the next step. And if it does appear in the neighborhood, then you just stay where you are. Okay. So you can check, again, the detail balance conditions and verify that the stationary distribution of this chain would be uniform. But of course, you need to assume that it's actually irreducible, and we're going to be assuming that Q is bigger than delta plus 1. Okay. Sorry. All right. So we're going to bound the mixing time of this chain using coupling. And just to recall, we had this theorem that if I have a coupling xt, yt of a Markov chain starting at some initial states x and y, and tau star is the first time that they meet, then the total variation distance can be bounded by the maximum over pairs of starting states of the probability that by time t you have not coupled. Okay. So our aim is going to be to bound this probability. So let me just write that here so we have it. And the theorem that we'll show is that if G has maximum degree delta and Q, the number of colors, is larger than 4 times delta, then the mixing time is of order n log n, and you see that there are some constants there. Okay. So here is the coupling that we're going to use. It's a very simple coupling. You generate a vertex color pair VK uniformly at random, and you update both copies of the chain, which are a pair of arbitrary colorings, by attempting to update the vertex V in both chains with the color K. And if you're able to do this, then you go ahead and do it. And if you're not, then you just stay where you are. Okay. All right. So let's analyze the coupling and try to see whether we can bound the probability that the time the time that they meet being bigger than t. Okay, so if I have two colorings at time t, xt and yt, I'm going to define a variable dt, which is going to be the number of vertices which have different colors in these two colorings. So I'll denote the color at a vertex v in the coloring xt by xt of v. Okay. Okay. And what we're going to do is use dt to track whether we've coupled or not. If we've coupled, then dt is 0. If we haven't coupled, then it will be bigger than 0. Right? Whereby we have coupled, I mean that the chains are in the same state. Okay. So we divide the analysis into two things that could happen. The vertex that you pick, either it could have the same color in both the chains, or it could have a different color. Okay. So first let's look at what happens if the vertex has a different color in the two chains. So here's an example of that. And now let's think about what would happen if you tried to update this vertex with the same color, right? That's our coupling. We pick the same color and try to update it in both. Well, you can see that the colors here are already different, so you're not going to increase dt by any more. Only two things could happen. Either dt stays the same or it decreases. Okay? And you'll see in the calculation that it won't really matter when it stays the same. What we're interested in is bounding the probability that it actually decreases. So in order for dt to decrease, we need to update it with the same color. And when can you do that? So you can do that if you happen to pick a color which doesn't occur in the neighborhood of either of these vertices. If you happen to pick a color like that, then you'll be able to update it in both of them. Okay? So I've crossed out the colors here which appear in either one of the neighborhoods. So we're left with these two colors. And you can see that if you pick them, either one of them, then dt will decrease. Now, the probability that what's the probability that you pick a pair of colors like this? So you have at most delta neighbors in the neighborhood of V. And so overall, there are 2 delta colors that you don't want to pick. And so you have a choice of Q minus 2 delta colors. So the overall probability that dt goes down by 1 can be lower bounded by the probability of, first of all, choosing a vertex that has a different color, which is dt over n, times the probability of choosing one of these good colors, which is q minus 2 delta over q. Okay? All right, so with this probability, we can guarantee that dt goes down. Okay, so let's see what happens in the other case when the 2 vertices have the same color. The vertex has the same color in both colorings. Okay, so in this case, the color is the same in both, so it can either go up or stay the same. We don't care when it stays the same, so let's just try to bound the probability that it would go up. Okay, so looking at this particular example, why would it happen that dt goes up? Well, you could pick one of the colors that occurs, say, in the neighborhood of this guy, say this light blue, right? And then if you tried to update this to light blue, you wouldn't be able to do it here, but you would be able to do it here. Okay? So certainly an upper bound on these bad colors is the number of colors that appear in the neighborhood of the vertex. Okay? So, all right, so how do we bound the probability of dt going up in this way? So I'm going to count it in a slightly funny way so I can get the bound in the form that I want. So I say the following, that overall in the 2 colorings, there are dt vertices where the color is different, right? And for those dt vertices, I have dt times delta vertices v that have the same color. That's an upper bound on the number of vertices v that have the same color and appear in the neighborhood of a vertex with different colors. Okay, and then I have a choice of 2 colors, for that vertex. So overall, that tells me that dt times 2 delta over qn is a bound on the probability of increasing dt. Okay, and hopefully you can convince yourself that that's really all that can happen. So we put this all together and we say, what's the expected change in dt in one step of this coupling? So you see that we go down with this probability at least, so that gives me this term, and we go up with this probability at most, so that gives me this term. And putting it all together, we have dt times 1 minus q minus 4 delta over n. And you notice that we're working under the assumption that q is bigger than 4 delta. And so this means that I'm getting something here which is less than 1. Okay, and that's kind of the crucial thing, that in one step of the coupling, the expected dt has decreased. Okay, so how do we use this? So let us iterate this argument. And if we did that, that would say that the expected value of dt, given some x naught, y naught, is bounded by the initial d0 times this factor this sort of contraction factor, 1 minus q minus 4 delta over qn to the power t. And if I just put an upper bound on d0 of n, then I get a factor like this, get a quantity like that. Okay? All right, and so I'm going to rewrite that a little bit more conveniently as n times, or bound it by n times exponential of minus of the quantity inside. So our theorem tells us that the total variation distance is bounded by the probability that you haven't coupled by time t. And this is equal to the probability that dt is still bigger than 1. Okay. By Markov's inequality, that's bounded by the expected value of dt. And so using that bound and asking for it to be less than or equal to epsilon, you would get that the mixing time is bounded by this thing. Okay, so are there any questions about that? All right. So that was a nice coupling argument, and so you can ask two things. Number one, is that the best we can do in terms of number of colors? So we said that if the number of colors is greater than 4 delta, then we have a bound on the mixing time. Can you do better than 4 delta? Okay, because we know that we have an irreducible chain for q being greater than delta plus 1. The second thing you can ask is, can you do better on the mixing time itself? Can you do something better than order n log n? So, so in fact, there are arguments by Hayes and Sinclair which show that you would need at least n log n, and roughly the intuition is that sort of by a coupon collector argument, by n log n. So if you go less than n log n, you haven't touched every vertex. You haven't chosen every vertex and updated its color, and so perhaps you haven't really randomized, every vertex. Of course, that doesn't mean that you haven't mixed, but that might be some sort of intuition for it. Okay, so the thing that I'll talk about next is an improvement to the number of colors. So this is this theorem that was shown by Jerem and Salas and Sokol, which says that if q is greater than 2 delta, then you can show that the mixing time of the metropolis chain is of order n log n. And the reason for doing this result is that it uses two new ingredients. So the first is that it uses sort of this idea of path metrics on the space of your colorings to simplify the proof, and so that you're able to make this coupling argument not for arbitrary states or arbitrary pairs of colorings, but actually just for pairs of colorings that differ at only one vertex in their color. And once you use this framework of the path metrics and focus on coupling just these special pairs of colorings, you see that you can do something a little bit more clever than just update the two vertices to the same color. And that's going to be the idea. Okay, so here's how you might think of coming up with this path metric idea. So recall what we've done so far is said that we have expected value of dt plus 1, and we've shown a contraction in it. So it's dt times e to the minus alpha for some constant alpha, which is bigger than 0. And that allowed us to say that the mixing time has this form. Okay? And I can maybe view this intuitively in the following way, that I had two arbitrary colorings, and dt was measuring somehow how different they were, right? So it was measuring how many vertices the colors are different at. So it's somehow measuring how different they are. And then I applied the coupling, and I got another pair of colors, and I could show that in expectation, dt plus 1 was smaller. Okay, so suppose it was the case that the fact that these two have dt vertices different. Suppose it was the case that that meant that you could actually move from this coloring to this coloring by changing the color of one vertex at a time, say in dt steps. So you can't actually do that, okay, always, but let's say you could. So the picture that I'm thinking of is something like this. So I've got these two colorings, and I've got these intermediate colorings here. Okay, and somehow intuitively it should be that if these two colorings differ in a large number of vertices, dt is big, then this path of colorings is kind of longer. Okay, and then I apply the coupling, and I got some contraction, and this distance is shorter. But what if I were to do the following thing? I apply the coupling to this pair and this pair, and I apply it to this pair and this pair, and so on. Okay, or I apply a coupling, a one-step coupling to this pair and this pair, and then I chain together all these couplings. So I'm being very vague here, but I chain together all these couplings and say, well, by the triangle inequality, if I get a contraction at each of these pairs, then overall I will get a contraction. Okay, something like that. So if we could all make that magically work somehow, then it would be enough just to bound the expected distance in one step of the coupling for these pairs that are close together. Okay, so that's the idea of path coupling, and here is kind of how you can actually do it. So path coupling was proposed by Bublé and Dyer. It works in the following way. So here I've denoted these squares are supposed to be states of the Markov chain, and the arrows denote the possible transitions between them. Okay, so there's some kind of graph which is induced by the transition matrix whose vertices are omega and whose edges I denote by k for kernel. Okay, so that's one graph that we have. So what we do is actually take the states of the Markov chain and define another graph on them. And the edges of this graph are called E0. Okay? And the edges of this graph, they need not have anything to do with the edges with the kernel. Okay? All right, so we define this graph, omega E naught. And we define a length function, so we assign a length xy, L of xy, to each edge xy in this graph. And the only restriction on L is that it has to be greater than or equal to 1. Okay. So you have this length function, and we're going to use it to define a path metric on the graph. So in particular, a path in this graph is just a sequence of states like this, x0 through xr, where each adjacent pair is an edge in the graph. The length of the path is defined to be the sum of the lengths of the edges, and then the path metric is just the shortest length path between two states. Okay. All right, so you have this path metric and this new graph, and the theorem that Bublé and Dyer proved is the following. So if for each edge xy in this graph, E naught, in this set of edges E naught, there's a coupling of the one-step distribution of the Markov chain. So you start at x and y, which are the endpoints of an edge in this graph, and you make the coupling, and you get out states x1 and y1, and you can show that the expected distance between them in this metric rho, given that you started at x and y, is e to the minus alpha times the original distance rho of xy. Then you have a bound on the mixing time of this form. And you can compare it to the bound on the mixing time that we had before, and you see that instead of n out here, we have log of the diameter in this metric. So the diameter is just the maximum distance between any pair of states. Okay, so that's the theorem. And what this lets you do is, just focus on nearby states and try to show that there's a contraction in the coupling there. So what I'm going to talk about is how to apply this theorem in order to show a bound on the mixing time in the case of colorings for the metropolis chain when Q is bigger than 2 delta. Okay. All right. So, we had this picture before where we started out with 2 colorings and the number of vertices that they differ at is dt. And what I'm going to try to do is turn this into a path metric. Okay. So this would be possible if I could take this coloring and move to this coloring through a sequence of, say, dt other colorings, maybe by changing one color at a time. But then the natural way to do this is just to look at a pair of vertices, and if you're red in one coloring and blue in the other, then change it from red to blue. But then you might violate the proper coloring constraint and end up with an improper coloring, right? Okay, so here is how you can get around this. So we have our graph G as before, and suppose omega tilde is the set of all colorings of G, so not just the proper ones, but also possibly improper ones. And let me think of what happens when I run the same Markov chain on this extended space omega tilde. Okay. So I select a vertex V and a color K uniformly, and if K is allowed at V, where now that means that the color K doesn't appear in the neighborhood of V, then I update the vertex to that color. So here's an example. I have an improper coloring, and I happen to pick that vertex. And the colors that are not allowed are red and orange, which appear in its neighborhood. But if I pick anything else, I'm allowed to update it. Okay. So, all right. So this is a Markov chain, and what you can argue is that the stationary distribution of this Markov chain will also be uniform on the set of all proper colorings. And what ends up happening is that if you start out with an improper coloring, when you're updating, you're always updating so that the neighbors of a vertex are now, properly colored with respect to it. Okay, so eventually you'll get rid of all the improper colors, and then you'll just be walking around on proper colorings. Okay. So what we're going to do actually is use path coupling to bound the mixing time of the Markov chain on omega tilde. And then, as we go through the argument, you should be able to see that you should also be able to bound the mixing time of the Markov chain on omega. But for now, we'll just focus on omega tilde. Okay, so all right. So let's set up the path coupling. So here's what you do. I'm going to define a graph on omega tilde. And I let x be adjacent to y if x and y differ in the color of exactly one vertex. Okay, and then I let L of xy be equal to 1 when x is adjacent to y. So now the path metric becomes exactly this dt when defined on omega tilde. Okay, so now we have to construct a coupling, and before we were just sort of given this coupling where we picked the same vertex and the same color and tried to update it in both. But let's try to come up with what could be a good coupling in this case. So when we do the case analysis, you'll see that it might be better to do something a bit different. So now there are two cases that we can divide things into. Suppose we start out by picking a uniformly random vertex. Okay, and let's say we pick the same vertex in both chains. Okay, so two things can happen. Either you pick the vertex which is where the color is different, or you pick a vertex where the color is the same. Okay, so here I've picked the differing vertex. And now if we try to understand what would happen, if we picked one color and tried to update it in both the chains at the same time. So let's see what would happen. Well, the neighborhood of both of these vertices is exactly the same, right? So if you happen to pick a color which already occurs in their neighborhoods, then you wouldn't be allowed to do it in either coloring and the distance wouldn't change. Okay. On the other hand, if you picked a color that was not in the neighborhood of the vertex V, then you would be allowed to update it in both colorings and you would decrease dt by 1. So that seems pretty good. And you can think about it and see that maybe there really isn't anything too much better that you could do. So the interesting thing happens in the second case, which is, there's another easy case too. So before we get to that, let's think about what would happen if you picked a vertex which was not a neighbor of one of the neighbors, which was not one of the neighbors of V. So we talked about what happens when you pick V, then there's these neighbors of V, and then there's all the other vertices. So suppose you pick one of those other vertices, then their colors are the same and their neighborhoods look exactly the same. So if you update them with the same color by picking a uniformly random color and updating them to the same color, then the distance wouldn't change at all. Okay. But where you could have the distance change is in the following situation, where you pick a neighbor of V. So the neighbor itself is colored the same thing in both the colorings, but it sees something different. So if you think about what would happen if you picked red here and tried to update the vertex W, you would fail to do so. But here, if you picked red at the same time and tried to update this, you would succeed. If you didn't have red in the neighborhood of W, that might happen. And so you would get one extra difference at W, and dt would go up. Okay. All right. So okay, that's too bad, but presumably it has to go up sometimes. And then let's think about what would happen if you picked yellow. So when you pick yellow, you fail in this case, and you succeed here, and again you create a difference. Okay. So there's two kind of choices where you create a difference. And in all other cases, when you perform the update, nothing happens to the distance. So the observation is that suppose we couple in the following way, that when you pick red here and it's not permitted to you, let us couple that with something that is not permitted here. And what is that? Picking yellow or orange, right? So if you pick orange here at the same time, then that's not permitted. You would fail to do it in both chains. You would end up not increasing dt. Okay, but now you have to make sure that you're actually doing a coupling, right? You have to make sure that this is an honest sort of step of the chain, and this is an honest step of the chain. So if you're saying when I choose red here, I choose yellow here, then you have to say when you choose yellow here, what happens here? So, you only have this one color left, so let's just see what happens if we say couple in the following way. If I choose yellow here, choose red here. And if you do that, well, you're going to update this with yellow, and you're going to update this with red, and you'll get a difference. dt will go up, right? Okay, but now you've gained something, because instead of having two choices where the distance went up, now you have one where it goes up and one where it just stays the same. Right? Okay, and that's where the gain comes from. So this is how we'll oops, and I wanted to show you that arrow. So this is how we'll define the coupling. So suppose that V is the disagreeing vertex in the two colorings. First start by picking some random vertex U and a color K uniformly. If the vertex U that you picked is not in the neighborhood of V, and that includes the vertex V, then just try to perform the same update in both chains. Okay. If U is in the neighborhood of V, then do the following thing. If the color that you picked isn't one of the ones that's different, so red or yellow, then you just attempt to update U with the color K in both chains. And the distance will not change. But if it is one of those colors, then you attempt to update U in X with the color K, but in the other chain with the other color, so the color which remains when you delete K from this set. Okay. All right. So now we can put all this together and write down what the expected change in distance will be. So we know that with probability at least Q minus delta divided by Qn, the distance will decrease, which comes from analyzing this case, because with probability 1 over n, you pick the differing vertex, and then you have Q minus delta choices for colors that don't appear in the neighborhood. So you get Q minus delta over Qn. And then if you're in this case, what happens? You are picking, so the bad case when the distance increases is when you are picking yellow here and red here. So that's exactly one color, right, out of Q possible colors. And this bad sort of scenario could happen in up to delta neighbors of the differing vertex. So you get a bound of delta over Qn for the probability of dt increasing. Okay? And so if you put those two together, you get Q minus of Q minus 2 delta over Qn, which will be negative when Q is bigger than 2n. So you plug this into the Bubbly-Dyer path coupling theorem. We've shown that there's a contraction, and that gives you the bound on the mixing time. And remember, the diameter of omega is, or omega tilde is bounded by n. So we're done. Okay. All right. So that's path coupling. So I'm going to end here the topic of colorings, and maybe just mention really quickly what the current state of this problem is. So it's conjectured that you should be able to show order n log n mixing as long as Q is bigger than or equal to delta plus 2. But n log, so you know, the best Q for which n log n mixing is known is this 2 delta. We know n squared log n mixing when Q is slightly below 2 delta. This is the result by Vigoda, showing when Q is bigger than 11 over 6 delta that you have polynomial mixing. And then this is the lower bound of Hayes and Sinclair that I mentioned before. And then there has been a lot of work trying to analyze the mixing time for the colorings chain in restricted cases, and trying to get fast n log n mixing for smaller values of delta. And the types of things that have been studied are things like triangle-free graphs and large bound on the maximum degree. And the reason for studying these sort of things comes from the picture that we had before. So if you look at this case where the distance is decreasing in the coupling, you see that it's good for you if you have a lot of colors here to choose from, which will decrease the distance, right? And in these triangle-free graphs and in these triangle-free graphs and graphs of large maximum degree, you can make arguments that at certain times, as you're running this chain, you will have a large number of colors available for you to update in both cases and decrease the distance. Other approaches that have been taken work with non-Markovian couplings. So all the couplings that we've seen so far are Markovian in the sense that when you define the coupling, you are defining it based on what your current pair of states is. Okay, and in general, if you define it based on the evolution of the pair of chains until now, that's a Markovian coupling. But remember that all you have to do is couple the distributions pt x dot and pt y dot, and potentially, you could look at evolutions of these chains, look at future states, and decide what the coupling should be at time t. So things like that are called non-Markovian couplings, and using those, people have also shown bounds on the mixing point. So this is work of Hayes and Vigoda. Yeah, so I've just put all these names here in a row because various combinations of them worked on these different cases. Okay, so in the last bit, I want to talk about some exact sampling algorithms. And so as I said in the beginning, the motivation for this might be that so far we've seen that you can get bounds on the total variation distance, but you might want to actually get exact samples using a Markov chain. So how can you do this type of thing? So here's an algorithm called coupling from the past, which was given by Propp and Wilson. And to motivate it, it's helpful to look at the following example and ask the following question. So suppose that we're looking at two evolutions of the same Markov chain. Maybe we're coupling them, and we run them until they come to the same state. Okay? You can ask, does that mean that the chain is at stationarity, right? So we've shown that it does mean that the total variation distance can be bounded. But does it mean that the variation distance to stationarity is 0? So here's an example which shows that that's not the case. So it's got two states, and you're moving out of A always with probability 1, and you're moving out of B with probability half, right? So you're going to be at B, twice as often in the long run, and that tells you that the stationary distribution is 1/3 and 2/3 on A and B. But if you think about running two copies of the chain, one started at A and one started from B, then you see that they would never meet at A, because when the chain is at A, it always moves to B right in the next step, right? So you can't meet at A. So the answer in this case is no, because A has probably 1/3 in the stationary distribution, but the chains never meet there. Okay. So here is kind of what one says about coupling from the past, CFTP. It happens to be the case that if in a certain sense you run the chain backwards or from the past, and I'll say what that is, it's just a phrase right now, from a certain time, so that from that time all the trajectories go and meet at one state, then in fact they're guaranteed to be drawn from the stationary distribution. Okay. So let's see how something like that could be set up. Okay, so I'm going to describe something called a random function representation of a Markov chain. So the setup is that you have an ergodic Markov chain with transition matrix P, and we're going to consider all functions that go from omega to omega. So they take a state in omega and they map it to another state in omega. And script f will be distributions over such functions. Okay? And a distribution over such functions will be called a random function representation if the probability when you draw a function according to script f and apply it to a state x, the probability that you get a state y is exactly the transition probability p of going from x to y. Okay. So let's take an example which will maybe make it clear. So let's consider the simple random walk that we saw last time. So remember, this is the walk where it's the random walk where I'm walking around on the interval, and I move up with probability half. I move down with probability half, but if I try to do it from the ends, then I just stay where I am. Right? Okay. And we'll come up with a random function representation for this Markov chain. So we're just going to use two functions, f and f prime. F of state I is defined to be the minimum of I plus 1 and n. So you just try to add 1 to I, but if you go over n, then you just stay at n. Right? And this is exactly what happens in the chain, right? And f prime of I is going to be the maximum of I minus 1 and 0, so you try to subtract 1, but if you become negative, you just stay at 0. And script f is going to be uniform on f and f prime. Okay. So I claim that now, p script probabilities, when the function is drawn from script f, that f of x is equal to y is exactly the transition probability of the simple random walk on the interval. Okay. So one result is that every transition matrix, in fact, has a random function representation. It need not be unique. There could be many ways you could define it. And we notice another thing, that the random function representation defines a coupling on omega in the following way, that if I take a pair of states and apply the same f to both of them, and I get f of x and f of y, then the states f of x and f of y are drawn according to the one-step distributions, right? So it is a coupling. Okay, and in fact, you could define this coupling on not just a pair of states, but all the states of the chain. Okay, so that's the random function representation, and it helps us set up coupling from the past in the following way. So you start out by taking all the times between minus infinity and infinity, and I'm going to think of the time 0 as the present, and negative times as the past, and positive times as the future. Okay. And to each one of these times, we're going to associate a random function ft, which is drawn from script f. Okay. And once you've drawn these functions, they're here to stay. So you just have this ft. Now, if I compose functions f0, f1 up to ft minus 1, then it's like applying the transition matrix t times, and I'm going to call this f0 of t applied to x. Okay, so this is a random state, and it satisfies the following property. The property that this random state is equal to some state y is just the t-step probability of being at y, given that you started at x. Okay, and now here is what we'll call the backward simulation of the chain from x. So you have the state x, and you apply to it f of minus t, apply to that f of minus t plus 1, etc., until you get to f of minus 1. So you end up at a random state, and actually, you can see that we haven't done anything very special. I mean, here we applied these t random functions, and here we applied another t random functions. Okay. So far nothing interesting has happened, but we just call that the backward simulation. Okay. So now let's look at the following thing. Suppose that capital S is a time, so that the following thing happens, that if I look at F0S, the forward simulation, but on all the states in omega. What does that mean? So F0, of any t of omega is just the set of states F0t of x for x in omega. Okay, so it's just a set of states. So suppose that capital S is the time, so that the size of this set becomes 1. Right? So if you think of the coupling view of this random function representation, it means that you look at these forward simulations of every state in omega, and you look at a time s when all of them have coalesced. Right? They've all become the same. And we've seen that in this case, you may not be at stationarity. Well, coupling from the past says that suppose instead you find a time capital S and look at this backwards evolution, okay, of omega, which is just defined to be the set of these random states. And you find a time capital S such that this is true. Then in that case, the chain is stationary. You are drawing from the stationary distribution. Okay. All right. So maybe I should clarify that a little bit. That f of minus s0 of omega is equal to some particular state, right? So let's call it x, and that state is drawn from the stationary distribution. So it's not too difficult to see why it works out. So let's just do the calculation. So we're going to assume the following fact, that if you look at f0 of t of x in the limit as t goes to infinity, then that's distributed according to the stationary distribution, right? That is just the forward evolution of the Markov chain. And if I look at f minus t0 of x with t going off to infinity, then that is also just an evolution of the chain, and it's also distributed according to the stationary distribution. Okay, so suppose that capital S is a time, so that this is true, and take any t which is bigger than s, so minus t is further back in time. All right. So let's try to calculate what the distribution of this state is, f minus t of 0. So you start at x, and you run the chain from minus t to 0. All right, so we apply it like this, and this just boils down to f of minus s of 0 applied to all this. Right? Okay, now all of this is just some random state. Let's call it y. And so you have f of minus s of 0 applied to some y. But we assumed that the size of this is 1. Okay, so no matter what you plug in here, you just get a single state out. So that means that f of minus s of 0 of y should be equal to f of minus s of 0 of x. Okay, so it's telling us that the distributions of these two things are the same. And since we chose t arbitrarily, f of minus t of 0 has the same distribution as f of minus infinity of 0, which is the stationary distribution. Okay. All right. So that's kind of the argument for why it works. How would you implement such a thing and get samples out of it? So here's like a implementation in a picture, and we've done it for this simple random walk chain. Okay, and the idea is very simple. What you do is you try to find this capital S. So you decide your functions ft for each time t, and then you start off at time minus 1, and you run copies of the chain started from all the possible, so maybe I should have labeled it, but these dots, they just represent 0, 1, up to n, the interval, right? So you start copies of the chain from all the possible states, and you do what your function tells you. So let's say that at time minus 1, we chose the function to be f prime, which means go down. So we do that to all of the states, and we end up at some new set of states. And if those chains have coalesced, then we found our capital S. Okay, if they have not, then what you do is you take one more time step back in time, and now you use the function for time 2, and then compose that with the function for time -1, and you see whether you've coalesced, and you haven't in this case. And here we can see that if you go back to -3 and the choice of our functions happen to be up, up, and down, then in fact at 0 you would go and coalesce. Okay, and now you're guaranteed that the sample that you've drawn is from stationary distribution.
So are we assuming here that the functions are bijective?
We're not assuming that the functions are bijective, and in fact, you can see that if you've got this state and this state, they go and meet. So maybe I didn't understand your question.
Yeah, maybe I didn't understand it either.
Okay. So the f's are just some functions from omega to omega, and I put in a state and I get out a state, and I can do that in any way that I want. Okay, so here are some of the issues with. So this seems really great. I mean, we just run copies of the chain like this and wait till they all coalesce, and everything seems good. But here are some issues. So this random function representation, it defines a coupling on the set of states, and choosing this random function representation is up to us, and it will affect how this random time S is distributed. So ideally, you would want to choose F so that your expected S is small, right? And you actually couple in a short amount of time. The second problem seems to be that we have to keep track of all of the states of the chain and look at all these trajectories. And for the random walk, maybe it's okay for the simple random walk on the interval. But let's say you have a very large state space like we had for colorings, or say the Ising model or Potts model or something, then you would have to keep track of all these trajectories. So that could be quite inefficient. But one of the benefits is that even if you don't have bounds on the mixing time, this gives you a way to get exact samples. Okay, and here is one observation which gets around these issues in a certain case. So this is monotone coupling from the past. So suppose there's a partial order on your set of states which is respected by the coupling. So this is something that we had in the simple random walk, right? Because if you have two states, one above the other, and then you apply this coupling, then one stays greater than or equal to the other. And suppose in addition you have a maximal state x max and a minimal state x min, then it's enough to just watch the trajectories started at x max and x min, right? Because everything else would stay in between, and once they converged, you'd be guaranteed that all of the trajectories have converged or coalesced. Okay, so this can actually be done, for example, in the Ising model, where you can define a partial order on the states, and the all plus and all minus configurations are the maximal and minimal states. And other models where you could do this are dimer configurations of a hexagonal grid and so bipartite independent sets. Okay, so I wanted to say maybe a tiny bit about the bound for the n log n bound for random shufflings, but I think I've kind of run out of time, so maybe I'll stop there.
Any questions?
Isn't it true that coupling from the past only seems to work in cases where you can prove some bound on the mixing time anyway?
That does seem to be the case. I haven't looked. So David Wilson has this huge page on problems recovering from the past. I haven't looked, but I think that is the case.
So what is the advantage then that you don't have an epsilon?
Well, let's see. So. Well, it might be the case that you don't have a bound. I mean, that's the one advantage that I can think of. So
Then it doesn't work.
It doesn't work in polynomial time. It works.
Sorry?
Doesn't work in polynomial time. It does work.
Well, it doesn't work in any feasible amount of time, it seems. I know Mark Jerram did some experiments with forests or the grid. If you ran it for, I think it was like a 20 by 20 grid, it was fine. But if you ran it on a 30 by 30 grid, it just ran forever, right? It just didn't couple. And it seems quite typical, I think.
yeah, I don't know of any examples.
The thing is, come on, it can't beat the mixing time. How could it? But it does. I mean, if it doesn't mix quickly, it won't converge quickly for sure. But it does give you an exact sample.
Yeah, but I mean, when is it important to have an exact sample?
I don't know. Practically, maybe you want to see what a random configuration looks like, or something like that.
Yeah, I mean, if you're doing something like sampling for approximate counting, it doesn't particularly matter that you haven't got an exact sample, right?
Well, any more questions? Well, otherwise, thank you.